Okay, we'd like to welcome you to our webinar today. Very pleased today to have representatives from University College Cork, Ocean Energy and University of Plymouth as well. Okay, I'd like to introduce Dr. Michael O'Shea from University College Cork, who will introduce the webinar and set out the agenda for today and give you an introduction to tank testing.
Thanks very much, Lisa. So welcome everyone to today's webinar. It's a star-studded lineup of speakers. And the full lineup is as follows. You'll have a little introduction to tank testing from myself, and it'll be focused on some of the work we're doing on the WEDUSEA project. And my colleague in University College Cork, William Flynn, will discuss some of the sensory implications and the measurement on board the full-scale device, as well as how we're utilising tank testing to size those and locate those. Then we'll move to Professor Tony Lewis, the CTO of Ocean Energy. He's going to discuss some of the work that OE have been undertaking, particularly around the deployment of devices. From there, we're going to move to our colleagues in Plymouth, who will discuss the mooring design. So that's Dr. Chen-Yu Zhao and Professor Lars Johanning. So without further ado, I'll get straight into my presentation. So wave energy demonstration at utility scale to enable arrays. That's the WEDUSEA project. I've heard about 5 different pronunciations of it. And on this webinar, I'm going to say WEDUSEA. So apologies to my colleagues if they pronounce it differently, and apologies to the audience if you hear different pronunciations of the project. So it's all based around the Ocean Energy 35 OE35 device, floating oscillating water column, the largest WEC in the world. And it's scalable and it can be built at scale. The latest version is more than 5 stories high, weighs over 800 tons, and the only moving parts are devices that sit well above the waves, making them much less prone to damage and corrosion when considering they're being deployed in very extreme environments. For the WEDUSEA project, the OE35 will operate in EMEC, and we'll talk about EMEC and where that's located. So I'll give you an idea of some of the size. We're talking about a draft of 8 meters, an overall length of 37.4 meters, a breadth of 18.49 meters, depth at the top of the superstructure of about 20 meters. So it's quite a big beast. So my topic today for this webinar is really about technology development and how we go through what are traditionally known as the TRL levels or technology readiness levels. Given the information I've just provided to you about the OE35, it's really at the TRL8 stage where it's being deployed, and we're now looking forward to array scale deployments. TRL levels originally came from NASA, who were developing technology and readiness technology for aerospace. In more recent years, we have the IEA, International Energy Agency, Ocean Energy Systems Group have developed a comparative type of metric for ocean energy devices, and they link in with the established TRL levels, but they have stages. So I would think that the WEDUSEA is at stage 4 commercial scale single device demonstration. That's where we are, which is equivalent to TRL 7 or 8. And that's the focus of this webinar. What I'm going to discuss is some tank testing, which you would actually take, potentially stage 1, stage 2, and even stage 3 for some design refinement. So the point I want to make really is all these are chronological stages, 1, 0 up to 5. Really, the development of a technology, and particularly in extreme locations, is never linear. It's always, I guess, you're moving between the stages for different aspects of your technology. For more information on how we look at ocean energy technology and how it's developed, design optimization, from concept creation to commercial array scale demonstration, there's been a recent publication, which is actually the 2nd edition of the OAS framework. So for a lot more information on how what we look at and what we test to go through these stages, there's quite a lot of information in that development. As I said, in WEDUSEA, we're at stage 4 essentially, which is commercial single scale device demonstration for the development, and the requirements at that stage, have some descriptive hallmarks. So open water testing, that's what we plan to do in EMEC, and I'll talk a little bit about that in a second. Sufficient duration of that testing, so we can look at these devices in over 12 months to get a full range of operating conditions, and particularly for a wave energy device to see how it survives in these challenging conditions. But also that first key one there, which I'm going to link to, is the further development and refinement of detailed numerical models and integrated subsystems to cover full operation envelope. So we're going to touch on that a little bit, and numerical and physical models. So A little bit about the WEDUSEA project. So the proposal is to install a OE35 device, as you've seen, in EMEC. And EMEC, for those who don't know, is at the very tip of Scotland. It's got a resource, but with that comes challenges in terms of the environment that we're actually going to deploy in for this project. And those challenges have led us to actually have to go back into the wave tank to look at the way to instrument and also to look at how we actually design the structure of the OE35 to withstand the large waves that we're hoping to harness the energy from. To give you an idea from theoretical background, there's lots of different ways to calculate the wave force on the hull. So, and unlike a traditional ship build, we have water on both sides on the OE device. So it makes it complicated, and as such, it's not a standardized procedure as you would have in naval architecture, because we're dealing with an oscillating water column, and one of the first of its kind at this scale. So we've had to go back into the tank to try and assess, well, how's the best way to measure this wave pressure, wave forces, and also where should we locate the sensors and what kind of pressure ranges should we be expecting, so we can select the correct sensors for the full-scale deployment. Because as a researcher, I suppose this is a very exciting time to be able to instrument one of these full-scale devices for the first time. This slide here just gives you an idea of, for the same wave conditions, this is the range of pressures you could expect depending on how you calculated using different design codes and different hydrodynamic formulas. So there's quite a lot of uncertainty around this area. Which brings us to physical modelling, and one of the ways we can address that gap or close that gap, we won't find the definitive answers, but we'll be able to close the gap in knowledge there, is through scale modelling, where we take a device such as the OE35 and we scale it down or we shrink it down, and we look at, how does it behave in a controlled environment, and how can we assess how it moves, how it vibrates, and how it reacts to the ocean conditions that it's going to be exposed to. So for similitude and scaling, to scale these devices down, we look at different types of scaling. So there's geometric similarity, so keeping the proportions of the device the same. There's kinematic similarity, which is looking at the motions and making sure the motions, such as in this case the wave motions, are scaled correctly. And then there's dynamic similarity, which looks at the force or the resultant of those motions and how they impact the device, which is quite a challenge, even in the most simplest of devices and simplest of environments. Perfect similarity isn't achievable, so we need to determine which forces are important and attempt to keep those force ratios the same, because you can't scale entirely to incorporate everything in the environment. And that's the challenge that we have in this project. How we address that is through tank testing. So I'm going to talk about two different tank testing, and my colleague William Flynn will talk a little bit more about some of the tank testing that we've undertaken. So one is here in Cork in UCC, which is the Deep Ocean Basin. It's 35 metre long, 3 metre deep, with active wave absorption paddles, and we can produce 1 metre waves at 25-second periods in fresh water. At a scale of 1:30, to go link back into the scaling, that would result in a prototype range of about 6 meters and a period range up to about 13 seconds for a 1/30th scale device. So it gives you an idea of what kind of size device you can fit in your tank. As it so happens, the OE buoy in various guises and forms has been developed over a variety of scales. As you go smaller in the scales, you have ever-reducing scale effects. So what we want to really do is get to a scale that will enable us to test and to capture the dynamics, particularly wave slamming and wave crashing is a very hard thing to scale. So that's something we're attempting to do in this project, is to try and capture those dynamics and then record that in the field. So this will give you an idea of how the scale and how the reducing effects can be reduced by going up in the scale. So we have a 1/50th, 1/30th scale model, 1/15th, 1/18th scale model in the picture. You go to a quarter scale, and then we have the OE35. This is actually a device that was installed in Hawaii, so it's the precursor to what we're looking at in the WEDUSEA project. I'll just give you a quick video which gives another idea of that.
So as we discussed so far, we've talked about scaling and the importance of following the correct TRL path and the scales. So you would work up from quite a large scaling ratio to something that would be full scale, and that's what we're doing in the WEDUSEA project, where we're actually demonstrating a full scale device. And that journey takes a long time. It goes from something like this. Now, this isn't a proof of concept device. This is a teaching device which just proves the concept of the oscillating water column, where you have this moving in a teaching flume, and it just shows the concept of the water going in through the orifice and then powering this fan here to That would be something like a 100 scale model. Here we have in front of us is a 30th scale model. So this is based on the WEDUSEA device itself. So this is being used to look at moorings design, and Lars will have a chat about that later on in terms of how they've used tank testing to refine and design the mooring system. That's 30th scale. In the tank behind us, we actually have a 15th scale device, which is tested all over the world in France, here in Cork. That's also been in America, testing in different tanks, different hydrodynamic properties. And one of the things we're going to try out here in the WEDUSEA project is we're going to try and design our sensors around capturing the motions that we capture here, and we can regulate here and compare that to what's happening in the field. And this is important for a good few reasons. One of the interesting things from a research point of view is the impact of wave slamming on the hulls here. So we're hoping to instrument the full-scale device with pressure sensors and force sensors to understand when those large waves roll in. There's been recordings of an 18-meter high wave in EMEC and Video Crew. What effect does that have on the mooring systems, on the power control, and on the hull integrity itself? So there are things we're interested to do, but we have to have the correct sensors. We have to have the sensors placed in the correct location in the hull to capture that. So we use a combination of numerical modeling, but also tank testing and tank trialing. And I think Will is going to talk a little bit more about the sensoring setup and the sensoring design and how we're using physical modeling to enable us to go further in the full-scale modeling. So,
and this is one of the devices that we have in the lab situation that obviously we don't have in a field situation in a deployment in the likes of EMEC. So I'll give you an idea of what kind of data we're recording when we're doing this tank testing.
Okay, so the setup inside the control room, basically controlling the waves. We're having all the data coming in here on these three screens. So on the far screen over there, you have what's happening at the paddle. So the guys have to tune the paddle to give whatever conditions, be them regular or irregular waves. What you put into the paddle then, you record in the basin. So I think here, are you recording wave heights here, is it?
Yeah, at the moment is the pressure sensor.
Okay, so these are the onboard pressure sensors.
You have load cells, forces here also.
The load cells on the moorings. So we have all the onboard data coming through here. And then if we move to this piece here, this is what we were talking about outside. So this is the Qualis output. This is the motion capture. So this is the cameras picking up the motion of those reflector balls on the device. And what we're hoping to do is when we put the IMU there is to correlate how the IMU and the accelerations change and compare that to the output of the Qualis system, which gives us the motions and the rotations. So as you can see, there's quite a lot of data being collected, even just in one test.
So that was in a controlled environment in Cork. We also tested the 15th or 18th scale, depending on what project we're talking about and what environment we're talking about, in Omset, New Jersey, under the Teamer program. So this is a 200-meter long outdoor wave tank. It has salt water, so it's saline, so slightly different buoyancy properties. So we wanted to do comparative testing here to see what the impact of both salinity was, but also different tank, different wave conditions to be able to test. So what we focused on in this testing was survivability. So being able to track the motions of the device using our inertial measurement unit without the Qualis system. So trying to develop algorithms, and Will talk a little bit more about that. So it gives you an idea of a different type of tank testing that we had to undertake as part of this project. So we've taken some of that data that we've recorded and are processing, and we're looking at in a numerical model, looking at where is the best place to place sensors. So as I mentioned earlier, this isn't like standard naval architecture where you have design codes where you can actually look at, okay, we have a tanker and this is the design pressure you design for. This is an open-ended design, so we have water on both sides of the hull. So it's quite a unique challenge. So we're gathering as much data, be it from finite element models, different wave tank testing campaigns, and trying to assess where can we put these sensor placements. So where can we put these sensors to really get the best data when the device does go to EMEC. So we're looking at scale models and looking at those results and trying to translate them upwards into the full scale device. There's a lot more detail on this work that we've done previously in a UTech paper from 2023, where we look at utilizing different materials and seeing how they react to in conditions similar to those that we're going to experience in EMEC in Scotland. So I'll hand you over now to William, who'll go into a little bit more detail on the sensor placement and design.
So I'm going to basically follow up on what Michael has just been speaking on, and that's regarding the sensoring on board the actual wave energy converter device. So in terms of the full-scale model, effectively, we're looking at the sensoring and signals. We're looking at primarily 5 sort of areas. Like you'd say the deck, the plenum chamber, machine room, which are obviously on the device. And then externally to this, we're looking at the moorings and also acoustic stations. And what I mean by acoustic stations are sort of basically stations for looking at acoustic noise and underwater. So again, this is just something similar to what Michael has shown. It's a CAD model design of the IE35, and I'm just illustrating here the areas in terms of the deck, plenum chamber, and machine room. So this is just a very quick sort of summary, I guess, or snapshot of the sensors on the actual device. As you would imagine, there are quite a lot of sensors that are utilized in terms of measuring, say, navigation, meteorological sensing, structural analysis, etc., and obviously all the electrical and power systems. This is just a very, I guess you could say, overview of what that is. So here, what I have is, I guess you could say, it's almost a pictorial view. So on board the device, you have your sensors. The output from these sensors will go to a data acquisition system. The purpose of the data acquisition system is obviously to digitize the signals and store those signals for analysis later. On the right-hand side of the picture, you can see there also are control aspects which are part of a PLC SCADA type system, which is from our project partners in Fraunhofer. And so collectively, what happens is that you have the data acquisition system acquiring sensors from, for example, meteorological sensors and low frequency, low sampling sensors going to the UCC DAC system. On the other side, you've got sensing, which is critical for the safe operation of the device, and logic, the control logic also for monitoring, say, conditions of valves, pumps, etc., going to our Fraunhofer DAC PLC SCADA system. On board is also obviously a camera system, and that's a separate sort of in terms of having its own dedicated server due to sort of bandwidth constraints and limitations. Collectively, that is all interfaced via HMI interface, and from the device, data is basically sent onshore via a umbilical cord. Obviously, data is first converted from copper to fiber, then transported and using the cable, and then onshore data is actually stored. From there, subsequent data remote access is provided. Externally to the onboard device, you have basically another data acquisition system that looks after the environmental and acoustic monitoring with onboard storage. And you also have some moorings looking at the applied loads and tensions. And that data is also fed and coupled to the onboard storage. So this, again, is just a quick overview of the sort of, I guess, more of the comms aspect. As I mentioned, there is this umbilical export cable that takes the data from the device to onshore, and it's basically stored locally in a sort of data server there. In the event of losing connectivity through that umbilical cord, we also have obviously as a backup comms service where we have a 4G router on board, and we also have the option of a CPE to CPE link that actually can send just critical data to another observation point that has a VLAN connected as well to the data switch room. So as Michael discussed earlier, in terms of sensor locations, it's quite challenging that given the number of sensors, where do you actually put them? A lot of the sensors, for example, on the deck, that's pretty straightforward in terms of these are sort of like weather stations, and as long as these are IP67 rated, they're all fine. But there are other sort of sensors that we need to know the strategic positions where to place them, especially if we're looking at, for example, in terms of pressure, structural integrity, wave forces, wave slamming, etc. So here I just give one example. It's looking at the basically structural integrity monitoring of the hull of the device in terms of where to actually locate sensors. obviously the front plate of the device. You got to remember that the motor of the OWC is facing away from the wave direction. And so the plate basically experiences the highest wave impact loading. So this would be an optimal place to locate the sensor. But given the extreme environmental conditions, sensor survivability would be very limited in this location if placing sensors on the actual plate itself. Also behind the plate, you have ballast tanks, and that water sloshing may cause interference. Another option somewhere that you potentially could put some of your, say, force sensors, pressure sensors here is on the roof of the plenum chamber. This is certainly a lot more sheltered, and so this would be a good location. Other constraints we also need to think of in terms of not just the extreme sort of environmental conditions, but also the physical location of the sensor, as we need to run cable lengths which are quite long back to the machine room where the actual control infrastructure is located. And that could be anything, in this case, for up to 50 meters away, which again, 50 meters of cable is quite expensive as well. If we go to the next slide, please. And here is another potential opportunity to put actual sensors for looking at force and motion, looking at wave impact, and as I said, structural integrity on a hull under the machine room, which is accessible from the machine room. And so this gives you a nice location where you could potentially put things, sensors. And in terms of distance and cabling, you're only 10 meters from the machine room. So this could be an example of a good location. I guess what I'm trying to show here is that the optimal location of sensors on device, it's basically, it's not that easy. You really need to sort of do some, I guess, investigations. And that's where, I guess you could say, our sort of scale model in the tank testing really comes in, where we can actually sort of look at optimum locations of sensors and actually use that then in the full scale development. So yes, so take us on to the scale model tank testing. Michael has already discussed this, but again, it's just in terms of to facilitate the wave energy technology, basically, and scaling up, actually tank testing is very important. And the output of testing can be used basically to further develop and demonstrate and optimize the full scale devices. So this here is the scale model of the OE15. I'm going to just talk about the actual sensoring on this and some of the tank testing that we've done. So Michael has already discussed about the fact is that we've done some tank testing at Lear, UCC in Cork, on the OE15 model. And we've also done some tank testing on the same model in OMSET in the USA, New Jersey. As Michael mentioned, the actual tank at UCC is a freshwater tank, measures about 35 meters, where in the OMSET tank in the USA it measures about 203 meters, and that's a salt water tank. So this is, again, Michael had actually shown this. It's just again, the outdoor saltwater tank at OMSET. So here we have the scaled model, the OE15 model, and you can see, compared to, it's quite, well, similar in some aspects of the full scale device. So this has been instrumented with different pressure sensors, Keller water pressure sensors, also some differential pressure sensors, and it's got also water level gauges. One thing that this sensor, or one thing that this scale model does have, in addition to what was previously tested in Lear, is an IMU sensor. And the IMU basically is for measuring the linear motion of the actual device. Again, here we see the actual scale model on the bridge of the tank before being actually put into the water. So this is a video in the same tank. Now, this is actually the OE30 scale model, but this will give you a quick idea of what we're trying to do here in Lear, where we have the Qualsys motion capture system.
So as previously discussed, what we have here is the Ocean Energy 30 scale model. What I'm holding here in my hand is effectively what's referred to as a reflector, a reflective bolt. And you can see here where it's being positioned around the actual device. In the actual test tank, what we have is an optical motion camera system. And what it does is detect the translation, rotation, and motion of the actual device. In the field, we don't have the luxury of having such series of devices. So what the plan is to use an actual IMU unit, which is an inertial measurement unit. Inside this, we have a triaxial accelerometer, gyroscope, and magnetometer, from which we can measure basically the 6 degrees of freedom. So roll, leaf, pitch, yaw, sway, surge, etc. This is mounted inside in the machine. What we would do during our tank testing is validate the IMU with the actual optical measurements that we actually see. Again, in the field, other measurements that we do the impact will be pressure, load, we will have temperature, pressure, also the cutting chamber, which is actually up here. We've got the machine room, which we've been measuring, so we're standing with area temperature. And we also have the input ducts, measuring more and more the temperature.
The message I was trying to get across was that in the field, we don't have the luxury of a Qualis's motion camera system. And we do have it in the layer tank. And basically, that's one of the main benefits of the layer Notif tank is that it does have this motion system that can track the motion of the device during wave tank testing for very different wave conditions and wave types. And you, by attaching these sort of capture markers at various location points on the device, you can see the camera and optical motion system can provide accurate information on the position, orientation of the model. And they can do this with the 6 degrees of freedom throughout the actual testing. So that's what the video basically was trying to illustrate there. So when we did the tank testing in OMSET, we didn't have this Qualisys system. What we used was this IMU unit. The IMU unit is a low-cost unit, and for these low-cost units, they generally don't provide direct information on the 6 degrees of freedom. They simply output a raw actual values of acceleration, velocity, and arbitrary units for the magnetometer. You can calculate the 3 degrees of rotation, which is obviously roll, pitch, and yaw, from these acceleration measurements, and then further derive the degrees of translation using sort of, I guess you could say, standard integration techniques, but this is quite problematic, and that introduces offset. There are ways you can do some sort of filtering to sort of, I guess, remove that, but it's still really not ideal. The IMU also doesn't provide any direct quaternion or Euler angle information output. You can actually sort of calculate this using sort of more of an ARGS fusion algorithms, but again, this isn't actually a trivial process. So what we're planning to do, well, it's actually ongoing, is that we're going to test the actual OE15 model again at layer, looking primarily at the analysis of displacement data and doing a motion analysis of the scale model. And so what we're having is that we have the Qualisys optical capture system. We also have the IMU data, so we can validate the numerical methodology used to derive the IMU 6 degrees of freedom, and obviously validate the data that was recorded at OMSET, so we can actually have the same tank conditions. And also, this is also used to demonstrate the viability of using a low-cost IMU unit as a mechanism for extracting device motions for the full-scale WEDUSEA device. And that's it, really. Thank you. Here is the WEDUSEA website if you want any further information on the project.
Next in our agenda to hear about the deployment and towing of the device from Professor Tony Lewis, Chief Technical Officer for Ocean Energy. Tony.
Okay, so Tony Lewis, Ocean Energy. What I want to talk about is really a very particular point associated with tank testing for the full-scale deployment. Michael has been talking about response of the device, and William talked a bit about that. What I want to talk about really is about the moorings, because the moorings are the most important part in terms of maintaining the device on station. The moorings affect the power production, and they also affect the survival. The moorings are a situation, in the case of the OE buoy, we have a catenary chain mooring. And the situation is with the catenary chain mooring, if we are scaling this catenary chain down to the model scale of 1 to 30, then the weight scales by a factor of 27,000. And the real problem then is that we cannot really find a model chain which is in the right scale for the full scale to really attach in the model testing. So that's where the conundrum is. How do we do that? Because in the left slide there, you can see the things that William was already talking about for motions, but we also have force transducers in the mooring lines to measure what the mooring forces are in this model. Now, the situation is then that the mooring, as I say, is a catenary mooring. And as you have the wave loading coming into the device, and the wave loading in the right side is in the plan in the model, comes from the top to the bottom of the picture on the right side. So the waves are coming downwards and pushing the model in the downwave direction, which applies then a load onto the mooring. And the mooring gives a restraint coming back. And the mooring is a bit like a spring, but the issue really is that it's a non-linear spring. The components of our mooring, and I think Jen Yu will talk a bit more about this in the design in the next presentation, but you can see that the load extension curve is a non-linear curve. It's not like a spring. A spring is just one single straight line, a linear line between force and extension. In the real mooring situation, we have this non-linear effect. So if we want to replace the mooring because we can't find a scaled chain by springs, we just cannot have one single spring, which then will give us the equivalent behavior, because the equivalent behavior is extremely important in terms of the responses and the power production. So how do we do that? And that's what I want to spend a little bit of time talking about, the detail of how we get this non-linear force extension curve in the model moorings. And we do that by a combination of springs in series. What this shows is, and I'll show a picture just after this, what we're doing is we're putting 5 sets of springs in series, and with that, then we're building up the force extension curve. Apologize, the axes are switched here, but it's the same situation. You have this non-linear behavior in the force extension curve, and the combination of springs in series operate like this. For the very small loads, spring number 1 is extending, and then when it gets up to 200 millimeters, we have a piece of string or rope which stops the spring extending more. So at 200 millimeters, spring 1 is at its full extension and stopped. And then spring 2, 3, 4, and 5 take over for the next bit. And then when the extension reaches 400 millimeters, we stop spring 2. And so on. We keep doing that. And then eventually, by building up the series of straight lines, we end up with a nonlinear curve for the overall mooring, which then has the relationship between load and extension as we want to model. Okay, so the next slide then shows the behavior of this mooring after we've done this modeling, if you like, with the springs and the stoppers, and it shows there the relationship between the force and extension, with the red dot, which you can just about see, being the target which we want for the actual model of the real mooring. This shows the 5 springs in spring sets, if you like. They're not individual springs. There are 5 spring sets in here. You can just about see. I'm not sure if you can point the springs. These are the silver. They're the silver things in the left-hand picture, and you can see there's a number of them then in series. And between either end of the spring, there is a cord of a fixed length, which allows the spring to extend to a certain amount. So in the first spring, it was 200 millimeters. In the second spring, it was another 200 millimeters, and so on. So we build up then the extension of this spring by pulling at either end, and the load extension curve becomes this non-linear situation. So on the right side, then you see the calibration undergoing in a simple calibration by hanging the spring set from a fixed point and then adding on weights. And when we do that and we add on weights, we have a lot of problems sometimes with the springs, because even though the manufacturer supplies the springs and says they're all exactly balanced, they're not all exactly the same stiffness, they're not all exactly the same pretension, and so on. So we have to select springs and then prove that they follow this model by adding weights to one end and following the extension. So this then shows the result of that, and the red line is the target line, and the other colored lines are the lines we're going to use in the model testing. And you can see that they're following in scale quite well the target applied from the calculations applied to the real mooring, which Chen Yu will talk about in a few minutes. We can be confident then that when we put these spring equivalents into the model and we send the waves at it, that when the wave forces are applied, the surge forces, the heave and the pitch will behave in scale in these model tests. We then clarify that because I'm not sure if you can remember the first picture. The mooring is splayed at about 40 degrees angle from the device to the mooring points. And if you think about it, the waves are going to cause the device to move in surge in a straight line away from the waves. So in the Orcaflex model, which Chen Yu will talk about, they calculate the surge of the device in the waves due to the mooring forces. So we do a calibration of that as well in the tank by simply pulling the device away from the waves in a linear series of steps with a winch and measuring its position with those marker points that Will talked about before. We can measure the position of the device in the tank in surge, and then we can compare that with the Orcaflex model in terms of the stiffness and the springiness, if you like, of the mooring system. So that shows then that the model will behave in a similar way as Michael was saying before. You apply the forces of dynamic similarity, then we end up with the similar effect in the resulting motions of the device, the heave, pitch, surge, and so on. Video already of the device in the waves, and as I say, then the motions and the response of the device will be in the response then will be in scale to the full scale prototype. The second, that was a very detailed aspect of the model testing, but it's the most important aspect of the model testing. Otherwise, you cannot validate your numerical models or really get an idea of how the device will behave in the real waves. The other aspect I just want to quickly talk about is the OE buoy, and Michael showed the dimensions before. The draft of the OE buoy is about 9 or 10 meters. And that causes some quite difficulties in terms of building the device and launching it in a particular shipyard, given the draft required. This was the launch from Portland in Oregon back in 2019. At that location, we were able to have the full draft at the location for launching, but there are many locations around the world where you only have limited water depth at the shipyard location. So the situation is that we have an option for applying a cofferdam to block the openings in the device and float the device without the tunnels flooded. And that means the device floats at a very shallow depth, but we were very worried about that option. You can do that with airbags or by blocking the ducts. And that allows you to build this device in a much wider range of locations. But we were rather worried about the stability of the naval architects were rather worried about the stability of the device in this reduced draft situation. So here you see some trials being done in the same wave tank on the stability in waves of the device just on location. In the next slide, I think it shows the situation of what will happen during a towing situation with the tug towing the device from the shipyard. The wave tank in Cork is able to act as a towing tank So the model can be towed along the tank using the instrument bridge, and this was a test to look at the stability of the device at this reduced draft in waves during the tow. And that turned out very well as well. So that really is another aspect of what you can use these model testings in the tank for informing the full scale design. So two aspects there: make sure you get the moorings right, and if you need any unusual towing situations, then tank testing can help with the deployment at full scale. Thank you very much for that, guys, and I'll hand then back to Chen Yu for the concluding presentation. Thank you.
Hello everyone, my name is Chen Yu Zhao from University of Plymouth. I'm the senior research fellow focused on the mooring system design. So today I will talk about the mooring system design just for the OE35 wave energy converter. Okay, this process has 4 parts, and I will firstly introduce some basic information of the OE35, and then introduce what is the mooring configuration for the device. After that, I will talk about the mooring design approach for this project, and then in the last, I will summarize the final mooring design. Okay, this is the entire mooring system of the OE35. This system starts with an anchor fixed on the seabed, providing the fundamental stabilities for the entire system. Attached to the anchor, it is the start and bottom chain, which lie flat on the seabed. It's started design as weight and prevent movement caused by the underwater currents and waves. Connected to the bottom chain, it is the startless top chain. The top chain is lighter and more flexible and rises towards to the surface. As the mooring line turns upward, and it connects with a nylon rope. The reason we choose the nylon rope because it's the strange and lightweight, and the more important is very, very flexible. So this design can help us to absorb the wave energy and the sharp increase the tension on the mooring line. So then a surface buoy is attached to provide the lift and reduce the strain on the lower section. Above the nylon rope, it is a Dyneema and polyester line. So the reason we choose that is because it's quite high strain and it's quite light. We use this connection to connect the buoy and the OE35 device. So we use a mooring design method which includes 3 different phases. So the first step is we run the multiple mooring simulations. This simulation result can help us to understand the maximum mooring land load under the different sea environment. And you may notice that we have the different sections have the mooring configuration. So that means that the stiffness of the whole mooring system may be non-linear. So in the first step, we also will understand the stiffness property of the whole system. In the second step is validate and to calibration. So we compared our simulation result and the tank test result. So we calibrate some numerical parameters to make it more accurate. In the last step, we will use the most validated configuration in the simulation, and we will then to perform the additional simulation to identify the maximum tension for the full-scale device. In the phase A, we use the Aqua Wave and Aqua Flex to do the simulation. The Aqua Wave will supply the K frequency result, and this result will be used for the Aqua Flex. All the non-linear properties include the mooring line properties and the device properties, and even the high order waveforce will be considered in the Aqua Flex. The output of the alcohol flags will include the hydrodynamic response of the device and the mooring load on the mooring lines. So this is the most extreme low environmental conditions for the simulations. Consider the OE35 will be tested in EMACT for just 2 years. So for the wave load, we use a 10 years return period. And for the other load, like the tidal current and the wind, which is not the most important load for the wave energy converters, we use a 5 years the return period. In the alcohol flag simulations, the simulation time can cover the 3 hours time. Even considered about the scaling ratios 3:1 in the tank text. The time required is still half an hour, which is too long for the tank test because it will produce a lot of the reflection wave. To address this challenge, we will select the wave series. We call it DLC 6.11. In this wave series, we can capture the highest wave height in the whole simulations, and this wave is believed to produce the peak tensions on the mooring line. So after scaled DLC 6.11, the time in the tank test is about 256 seconds. But the tank-to-weight limitation made it impossible to directly scale each component of the OE35 mooring system. To address this challenge, we will focus on the horizontal stiffness of the whole system. So in the simulations, we give some the forced motion, and then we can say we give the forced motion in the horizontal direction, and we calculate the stiffness based on the motion, strain, and the tension in the simulations. So under this method, so our anchor point will not be limited on the seabed. The anchor point in the tank test will be installed on the side wall of the tank. To get the similar horizontal stiffness, so in the tank test, we use the different springs combinations. So between these springs, we added some stoppers to prevent the springs to overextend. So this result shows the horizontal stiffness curve in the alcohol flags and the tank test. You can see it's matched very well. This is the result from simulation and the tank test. I can find that for the motions, the results can match well. And for the low tensions, the simulation match well too. But for the very peak tension, it seems like the simulation overestimated the peak tension. So there may cause two reasons. The first reason, we didn't consider the buoys in the tank test, and the second reason probably be more important because we added some stoppers between the springs to prevent its overextend. But in the realities, some materials like rubber, like nylon, will become very stiff when it's overextend and produce very high tensions. So because of the limitations, we cannot cover the exactly same stiffness when we face the very high, very peak tensions. So these two reasons cause the difference. But generally, the result from tank test and numerical simulations can satisfy the accurate requirement for the future research. After the validations, so we use the simulation result to final design the mooring system. So as we can see, the height tension in all mooring lines is about 2,000 kilonewtons. And for the drift, we have about 20 meters on Y direction, and in X direction, we have about 5 meters offset. So all these numbers can meet the future sea trail limitations in the EMAC. We also checked the anchor lift angle and the anchor tensions. So in the whole simulations, even in the most extreme ones, the anchor the anchor is not fully up, it's still lay on the seabed, it also meet the requirement of the operation. So I also found use the maximum tension to design the anchor size of the anchor properties. The final mooring designs based on the simulation results and some industrial result. So in the final designs, we added some shackles to connect the different sections, and we also added some of the safety lines to make the whole system more reliable. Okay, this is my presentation today, and thanks for your attention.
That's great. Thank you very much, Chenyu. So that concludes all our presentations for today. Now I would like to thank everybody, thank the panel for all their presentations today. Obviously, you can find out more information about our project through our website, which is frequently updated, so www.wedusea.com. We've got sections on there, including things like news, blogs, and events, where you'll find some of the WEDUSEA team at upcoming events that they may be attending. And we also have weekly updates on LinkedIn on our project as well. So feel free to follow us and find out some more information. Okay, thank you very much for joining today.